Welcome to this exploration of one of the most fascinating phenomena in physics, the sonic boom. Today, we'll discover what happens when objects break the sound barrier and create powerful shock waves that can rattle windows and shake the ground beneath us. Before we understand sonic booms, we need to know what sound actually is. Sound travels through air as pressure waves, created by compression and expansion of air molecules. These waves move at a specific speed, approximately 343 meters per second at sea level when the temperature is 20 degrees Celsius. This speed is what we call the speed of sound. To describe how fast an object moves relative to sound, scientists use the Mach number. The formula is simple. Mach equals velocity divided by the speed of sound. When an object travels slower than sound, we call it subsonic, with a Mach number less than 1. At exactly the speed of sound, it's transonic, with Mach approximately equal to 1. And when it exceeds the speed of sound, it's supersonic, with a Mach number greater than 1. During subsonic flight, when Mach is less than 1, the aircraft moves slower than its own sound waves. The pressure waves created by the aircraft spread evenly in all directions, moving away from the plane like ripples on water. The air ahead of the aircraft receives advance warning of its approach and smoothly flows out of the way. As an aircraft approaches the speed of sound, when Mach is approximately equal to 1, something dramatic begins to happen. The sound waves start to bunch up ahead of the aircraft because they can't escape fast enough. Pressure builds in front of the plane as the waves pile up, creating what we call the sound barrier. The aircraft is essentially catching up to its own sound waves. When the aircraft breaks through and flies supersonic, with Mach greater than 1, it actually outruns its own sound waves. The aircraft is now moving faster than sound can propagate through the air. This creates a cone-shaped shock wave that trails behind the aircraft, similar to the wake left by a boat moving faster than water waves. The angle of this shock wave cone is mathematically determined by the formula. Sine of the angle equals 1 divided by the Mach number. This relationship tells us something interesting. The higher the speed, the narrower the cone angle becomes. Conversely, at lower supersonic speeds, the cone angle is wider. This cone angle is crucial in understanding where sonic booms will be heard on the ground. So what exactly creates that thunderous boom we hear? The shock wave is a sudden, sharp boundary where air pressure changes dramatically. As this cone-shaped shock wave sweeps across the ground below the aircraft's flight path, observers experience a rapid pressure spike. This sudden change in air pressure is what we perceive as the sonic boom, a sound similar to an explosion or thunder. Sonic booms have several unique characteristics. First, they typically produce a double bang, created by shock waves from both the nose and tail of the aircraft. Second, the boom is generated continuously throughout the entire supersonic flight, not just when breaking the barrier. Third, it creates a carpet effect, affecting a wide area along the entire flight path below the aircraft. Finally, the intensity can be powerful enough to rattle windows and even damage structures on the ground. Let's recap the key points. First, a sonic boom occurs when an object exceeds the speed of sound. Second, shock waves form cone-shaped pressure boundaries trailing the supersonic object. Third, the cone angle depends directly on the Mach number of the aircraft, getting narrower as speed increases. And finally, the boom is not a one-time event, but a continuous phenomenon that persists throughout the entire supersonic flight, creating a trail of thunder wherever the aircraft flies.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.